Okay, so welcome back, and we continue with from Manchester. We'll tell us about the standard model categories for infinite groups.
Cool, great. So thanks a lot for coming. I know it's Friday afternoon, so we'll be all a bit tired by now. So yeah, I want to talk about the stable category, specifically for infinite groups. But before I do that, I will just talk about what the stable module category is for finite groups, so how it's kind of classically defined in case people haven't seen that before. So we take a finite group G, we take a field of characteristic P, and we want P to divide the order of the group because it's not interesting if it's not in the modular case. And what we want to do is we want to kill all the projective modules. And so to do this, we don't change the object, we change the morphisms in the category. So we consider all KG modules. And so this includes all the kind of infinitely generated ones as well. But then with the morphisms, we put this equivalence relation where we identify two of the morphisms if they're different factors to a projective. And so this means that if we take the identity map on any projective, this will just be equivalent to 0. So the projective is stably isomorphic to 0. And so in this way, we've killed all the projectives and we've only killed the projectives. And so you might ask, why would you want to do this? So this, I actually don't know the history of this particularly, but it goes back like 40, 50 years probably. And one motivation might be that we can view elements of tape cohomology just as morphisms in this category. And so it becomes quite a natural home for a lot of these sort of questions. And yeah, it's been studied over finite groups for by many people, and it's got a lot of pretty nice properties, but for us, the interesting one is going to be that it's a tensor triangulated category. And so these kind of somehow we can think of these as some category version of the rings. And so the triangulated structure, this just comes from the short exact sequences of the modules. These descend to give exact triangles. The tensor product over K with the bag and the G action, this descends to a well-defined functor on the stable category. And it's a triangulated functor as well. And it has a tensor unit. So we just look at the field K, trivial G action. We tensor that with any module M, you get something that's naturally isomorphic to M. And yeah, this is what we're going to want when we move to an infinite. And so we can ask, well, why can't we just do this for G infinite? And obviously we can, but the issue is that it's not going to be triangulated if the group's infinite. And so it'll be like left triangulated, but that's just not a very interesting property. And so we need to somehow generalize this in a different way. But before I explain how we can do that, I'm just going to talk about the groups that we're interested in. So these were defined by Peter Kropholler in the 90s. And it's this kind of hierarchical definition. And I'm not going to put the exact definition up because it's not very useful. But the point is, we start with these H0 groups as a base layer, and these are just all finite groups. And then we define, for every ordinal, we define the alpha kind of step of this hierarchy inductively, so based on everything that comes below it. And then we say it's an HF group, but it's at some point in this hierarchy. And what we're actually going to be interested in is locally HF groups, so these are LHF groups. And they're just groups where every finitely generated subgroup is in the hierarchy in some stage. And obviously, if you started with the finite groups, you can kind of hope that the representation theory of these LHF groups will depend on the finite subgroups. And so if we choose our property carefully, we can take something that holds over finite groups and just induct our way all the way up this hierarchy to get it for all LHF groups. And that turns out to be, yeah, pretty powerful if you choose the right property. So, yeah, there's many examples of LHF groups. These are just a few that are taken from Kropholler's original paper, because I didn't want to go searching for more examples, but there are plenty of examples that you can find. So we have groups of finite virtual cohomological dimension. And I think earlier in the week, in one of the talks, we saw the notion of a classifying space in proper actions. And if a group has a finite dimensional model for this, it will also be an LHF, it will be an 81F impact. We have groups which have finite index soluble subgroups, linear groups over fields, and yeah, plenty more. But it's not kind of every single group ever. And the classic example is Thompson's group, which this is a presentation for, which won't be an LHF group. And again, there's plenty more examples that have been constructed that won't lie in this hierarchy, but they're slightly more complicated to explain how we construct them. So to define the stable category, we're going to restrict ourselves to these special modules called Golden-Stein projectives, which somehow these have nice cohomological properties. And so a module is Golden-Stein projective if it's the kernel in an exact complex of projectives. And we need this complex to remain exact when we form it into some projective Q. And so this extra kind of condition with the whole is called total acyclicity. And it ensures that these sort of resolutions will be unique up the homotopy. But actually, we don't need it for LHF groups. So then Bediotti and Tilelli have shown that we get it for free. So we can just think of Golden-Stein projectives as kernels in exact complexes of projectives, which makes things kind of a lot easier to work with. We're not constantly checking this extra property. And so we have, yeah, the example here, every projective module is Golden-Stein projective, so remains a good one. We can just take this crude term, exact sequence with the identity map in the middle. And maybe more interesting, if we go back to our book being finite over a field, then every module will be Golden-Stein projective, because we can just take a projective resolution and an injective resolution and shove them together. And so yeah, we're really kind of generalizing that property. But obviously over an infinite group, there will be non-Golden-Stein projective modules. Great, and so this is what we're going to use to define the stable category. And the very nice thing is the category of Golden-Stein projectives is going to be a Frobenius category over anything. And so what this means is that we can just mod out by the projectives in exactly the same way as before, and we're always going to get a triangulated category. And so this is our kind of our candidate. And using this this result from the last page with, by Begiotti and Tilelli, it's very easy to show that the tensor product of two Golden-Stein projectives is itself Golden-Stein projective, because you just have an exact complex of projectives that you tensor, and you get an exact complex of projectives with the right kernel. And so we're almost there, but there is a slight kind of stumbling block, which is that there's not a particularly obvious unit for the tensor product. So before it was just the trivial module K, but if we have an infinite group, this will never be a Golden-Stein projective module, so it's never going to live in the right category. And so what we need to do is we somehow need to approximate modules by suitable Golden-Stein projectives so that they behave close enough, and then we use that approximation as the tensor unit. These are called special pre-covers in general, if you've ever seen them. And you basically, I'm not going to do it, but you can show that these exist over LHF groups, and that uses that they exist over finite groups, and then we just build our way up. And so then we can take this approximation of the trivial module, and we get a tensor triangulated category.
Is it true that the option to break it all with tensor idea?
They what, sorry?
They form tensor idea. You take one module with this property and you tensor it with some other module. It's something that is called
What, is it tensoring with another module? No, not in general. No. If it's 3 over K, it will be.
Okay.
Well, yeah, I could say that. Yeah, you can do it more generally, but yeah, obviously it's material, then yeah, that's true. Cool. So Yeah, this isn't very important, but there's other ways we can construct this category, and they're all going to be equivalent, and there's actually more that I've not written down. But so we can put a nice kind of monoidal model structure on the category of modules, and then this is just going to be the homotopy category where the co-fragments are the Golden-Stein projectives. We have this quotient of a derived category, and yeah, as I said, there's others. But I do want to point out, so Nadia, Maxa, and Pete Simons for, well, for H1F groups, they show that this will be equivalent to the singularity category, which is this quotient of the derived category. That is not true for general LHF group. That's something quite special about this kind of first stage in the hierarchy.
Just a quick question. For the first bullet there, does that work with Gillespie? Jimmy Gillespie?
It's not very related to that, basically. And it's using his his Markovi theories about kind of complete closure pairs. Of course, I think this is the only bit of color in the presentation because it's that important. But we have this very special property of the stable category, which somehow generalizes Chouinard's theorem, and you've seen that for finite groups. And it means that we can detect being stably isomorphic to zero just on the finite subgroups. So if X restricted to every finite subgroup has finite projective dimension, then it's going to be stably zero. And then that means that X itself is isomorphic to zero. And we'll use this again later, but for now I want to point out that if we have a torsion-free group, this means that the stable category will just be zero. And so basically there's nothing interesting that I'm going to say in that case. So we want, and if we're working over a field, we're going to want some non-trivial key torsion happening. And this gives us an example of a group where the stable category is not going to be the singularity category. The stable category is zero, the singularity category isn't. Great, so we have our tensor triangulated category. And if you're that way inclined, there's a lot of questions that you might ask about such a category. And so I'll start off, well, I'll try and answer some of them in the rest of the talk. And we'll start talking about localizing tensor ideals. So these are kind of like monoidal localizations of the category, if you like that way of thinking. But for us, we can just think of them as subcategories S, which are triangulated. We need them to be closed under infinite coproducts, which just, these are just direct sums of modules. And we need them to be tensor ideals. And so this is like a, well, yeah, as you had said, it's like an ideal in a ring. We need it to be closed under tensor with any. And basically what we want to do is we want to classify all of these, see if we can understand them. So for every module M, we can just look at the smallest localizing ideal that contains it. And we can think of all the other modules in this ideal generated by M and somehow being built out of M. So we started with M, taken like some co-products and extensions and quotients and tensors, and we've got N. And so by classifying these, it somehow gives us a weaker classification of the KG modules. Obviously, we can't classify all modules, all modular representations, but this gives us a broader type of classification. So, well, why might this be possible? So Benson, Iyengar, and Krause basically have done this for finite groups. And they released a series of papers in which they develop a lot of machinery to prove these sort of classification theorems in general contexts. And it culminates in this paper on the stable category for a finite group. And they prove this, and it's very non-trivial what they do, and it's very clever. So just to state it, first, if we take the cohomology ring, this will be a graded ring. And so this means we can look at the homogeneous prime ideals of it, and we can take them just as a set. And then there's a very big ideal, which consists of everything in the positive grading, the maximal ideal. And so we just throw that out. We don't want that. And then we call this approach. And so for now, this is just a set. There's no topology, there's nothing. We just have a bunch of prime ideals. And so the result by Benson, Iyengar, and Krause is that the localizing ideals of the stable category are in bijection with subsets of the spectrum of the cohomology thing. Which is very cool and probably quite unexpected. And so I should add, by work with Quillen for like the 70s, this spectrum of the cohomology ring, this is pretty well understood. This is, yeah, something we can really get a grip on if we want. And so, yeah, we can lift this to the module category if you want to, where everything is just defined in a kind of obvious way. But the problem is, so as I said, they develop a lot of theory, but LHF groups, the stable category, we can't just shove this into their machinery because it doesn't fit, it doesn't satisfy all the assumptions that they need. So we need to somehow do something else. And so the obvious thing to try and do is we take localizing ideals for our big LHF group and we just restrict it down to the finite subgroups. And then we use this theorem. And basically this works once you go through all the details. So the idea here is we can take a localizing ideal for our group G and we can restrict it to a finite subgroup. But now this won't be a triangulated subcategory, so we have to look at the localizing ideal generated by all these restrictions. And if we do this to every finite subgroup, then we get kind of compatibility relations. So if we have an inclusion between two finite subgroups, then, and we restrict to one and then the smaller one, we may as well have just restricted to the smaller one, we're going to get the same thing. And similarly, if we have conjugate subgroups, then, and we restrict to one and we restrict to the other, these are just going to be conjugated ideals where we've literally just taken all of the modules and conjugated them. And so that's what a compatible family is. It's a collection of ideals in the stable categories for all the finite subgroups that satisfy these sort of compatibility. And it turns out that doing this restriction to the finite groups is a bijection. And so we only need to understand how everything works from the finite subgroups and maybe somehow reconstruct it back up in the group G. So I just want to say the idea of the proof very quickly. And so you can write down an explicit inverse. And to show that inverses, you need to show that kind of inverses on both sides, obviously. And so the first bullet point here, this is saying kind of morally that given a module n, we can reconstruct it, or at least the localizing ideal it generates, just by knowing how it acts, how it works when we restrict it to every finite subgroup. And to show this is true, we use this property that being zero, being stably zero, is detected in finite subgroups. So you kind of only need to show this for things which are isomorphic to zero, and then you get it for all KG modules. And then that shows it's kind of one side an inverse, and to show it's an inverse on the other side, all you need is a Mackey decomposition formula. So when you induce and then restrict, the module just decomposes as a sum of kind of a bunch of conjugates restricted and reduced. So the reason I wanted to talk about the proof is because it's kind of stupid. You don't really need much for it, which means that you can generalize it. And so this is my very kind of brief part on the higher structures. Because what we need for this proof to work is we need categories for all the groups. We need this kind of restriction, induction, adjunction. We need this Mackey formula. We need a projection formula. So this just means the tensor product kind of behaves nicely with restriction and induction. And then we have this property that being zero is detected on finite subgroups, which we don't strictly need, but it makes things a lot nicer. And we can formalize this two-factorially. And actually, a lot of the ideas have already been done by Balmer and and they have this idea of a Mackey two-function, a green two-function really, because we have the tensor product. And I'm not going to write the definition because it's not very nice, but it gives us this. And it's essentially the definition of a Mackey function, except we have categories rather than a being groups coming out. So yeah, we can work in this kind of slightly more general setting if we want to. Great, so what we've done there didn't actually use Benson, Iyengar, and Krause's result form. So now we can kind of pull that in and get in terms of the cohomology rings. And so we take a category where the objects are just finite subgroups, and then the morphisms are kind of inclusions and conjugations. These inclusions and conjugations induce maps on these spectra, and we can take the colimit. And then subsets of this colimit are going to be in correspondence with the localizing fields. And if we have a group where Quillen's stratification theorem holds, so it's like finite virtual cohomological dimension, this colimit, we can just identify it with the spectrum of the cohomology ring. So we get really, it's the same statement as for finite groups. And so, yeah, this is quite nice because if we're working over a field of characteristic P, we can reduce to all the elementary abelians. And in this case, the spectra are just projective spaces. So we're just gluing together a bunch of projective spaces, really depending on the subgroup structure of G. Cool, so I'll just go through, a quick example. So this is kind of the easiest example you can think of, because it means I don't have to draw anything too complicated on LaTeX, which I can't do. So we take a free product of two cyclic groups of order P, and then we know that every finite subgroup is either a trivial subgroup or it's conjugate to exactly one of these factors. We also know that the spectrum of the cohomology ring of cyclic groups are just points. And so then, from what we just said, there's a bijection between the localizing ideals and subsets are just a disjoint union of 2 points. So this gives us 4 localizing ideals. And actually, if you work kind of back through it, you can get this description in terms of the modules. So you have the 0 ideal, the whole category, and then you can look at all modules which restrict from the first factor to something projective, and then do something else in the other factor, and vice versa. And these kind of describe this localizing ideals. So if we wanted to take like an amalgamated P product or an H&N extension or something like that, we can, but it's going to be a bit more work. Or we can take F and E to be slightly more interesting groups. But I think this illustrates, as I said, in the easiest possible way. Cool, so that's the first question about tensor triangulated categories, and the second one is the dual question. So it's not maybe entirely clear from what I said, but the category has products, and the tensor product has a right adjoint, which is called the internal form. And so we can define a co-localizing co-ideal just as something that's closed under products and closed under the internal form. And then we can ask, well, can we classify these things? And it turns out, yes, we can. So the finite groups, this is proven again by Benson, Iyengar, and Krause. You have a bijection between the localizing tensor ideals and the co-localizing co-ideals. And it's an explicit bijection. And we can extend that to all NHF groups. Again, basically, you just reduce these co-localizing co-ideals down to the finite subgroups. Great, so I won't say more about that. What I want to talk about finally is the spectrum of the category. So this was defined by Balmer, I think about 20 years ago. So you take an essentially small tensor triangulated category, which I'll say more about in a second, and he defines the spectrum of prime ideals. And these, it's literally like the spectrum of a ring of prime ideals. You look at fixed tensor ideals, which have this primality condition with the tensor product. So if M tensor N is in P, then either N is in P or N is in P. And so this is it in a set, just these prime ideals, and he puts a topology on it, which I won't go into. But the interesting thing is, it's called the final support data of the category. It's somehow a universal solution to a classification problem of the category. And there's a whole industry of calculating spectra of different categories. that I'm sure many of you are familiar with. So I won't say more about why you might want to do it. You'll have to believe that it's something interesting. But the problem is, yeah, it's for something essentially small, so we can't use the whole stable category. What we have to do is look at kind of the finite, the small objects of it. So for finite groups, this just corresponds to the finitely generated modules. And so Benson, Carlson, and Rickard proved in different language, but what they essentially proved was that the spectrum of the category, the stable category of finitely generated modules, will be homeomorphic in whatever the topology is to the spectrum of the cohomology grain. And then this theorem actually this precedes the work of Balmer and the work of Benson, Iyengar, and Krause that we saw earlier. So I'm kind of working historically backwards. And so if we have an infinite group, it's not clear what the correct replacement of finitely generated modules are. So these won't form a triangulated subcategory, for example, because over an infinite group, if you take a kind of an epimorphism of finitely generated modules, you're not going to get something finitely generated as a kernel. And there's various different notions in triangulated categories that we might use as being small or being finite. And so two in particular are being compact and being rigid. And so the definition is not too important. But for finite groups, these are the same, and they're just the finitely generated modules. But as soon as you let them be infinite, they can be very different, actually, and they'll very, very rarely coincide. And so this is what it means when it says that it's not going to be rigidly compactly generated. And this can happen even for H1F groups. So in the first layer of the hierarchy, we already get that the behavior is quite different. It's a lot less nice in this sense. And also, yeah, the tensor unit doesn't have to be a compact object, which again is kind of strange and quite different to the case of finite groups. And so, yeah, what we want to use is the rigid objects. So we can think of these are modules which will be stably finitely generated when we restrict to any finite subgroup. And you can see these are different. They're compact objects. Somehow in our mind, we should think of these as FP infinity modules. So these are modules which have resolution by finitely generated projectives. And yeah, there's no reason restriction from an infinite group to a finite subgroup is going to preserve finite generation. So we wouldn't expect the rigids and the compacts to be the same in general. And so yeah, the rigid objects, these form a nice kind of thick tensor ideal like those under tensoring. And so that's what we have to use. And what we can get the spectrum of the stable category, but it's much more kind of restricted classic groups. So we have H1F groups of type FP infinity. So these are where the trivial module has a resolution by finitely generated projectives. And then we get the same statement basically as the finite group. So the spectrum is homeomorphic to the spectrum of the cohomology ring. And this really comes from, we take the classification of localizing tensor ideals from before, we restrict it to the rigid objects, and that kind of somehow gives us this homeomorphism. And I didn't write it up because I'm not entirely sure, but I don't think that this is true for a general LHF group. And you probably wouldn't expect it to be in general. But yeah, I don't want to completely claim that. And I think that is, yeah, everything I have to say. So thank you.
Yeah, so going back to my question before about sort of Gillespie's stuff, Gillespie, can you tell us about the rating properties of this, KG, where G is an infinite group? I mean, it's not a course, right?
No, it's not. It will be for like H1, for example. But yeah, I know it's not very nice. It's kind of very special that we can use the finite subgroups as the building block for these groups. But no, it's not Golden-Stein, it's not, yeah, I don't know of any particularly nice property that it does have. Yeah.
Any more questions? So let's say instead of starting with finite groups, you can just start with something like, let's say, T groups, finite T groups. So you get something different.
So if you're working over a field characteristic P, no, I don't think so, because you can reduce always to the elementary abelian, yeah, case. But if you're working with a Z or something, no, you would need all finite groups. Yeah.
Very so, then it's completed. Yeah.